there are two big changes in compute paradigm which I think will drive wealth creation in the future. One is Moore's law is ending. We have to be smarter about simplifying logic down to the gate level to get more out of the systems, because we can't cramp just more gates on silicon. So we have to be smarter above in the more higher abstraction levels of the stack. Second, we have data-centric compute. In other words, instead of writing explicit programs and executing them, we have data which is driving algorithms which then execute. So this is the big change. Both of these drivers are massive opportunities for wealth creation because it's a change of compute paradigms. This is the Not Even Wrong podcast. It's September 17th, 2022. This is Krim Delco. It's a Saturday. There's no update. For the year, we are down 24.7%. The market's down 18.7%. We're underperforming by 6%. So I want to talk about two massive shifts in compute paradigms, which, by the way, got reiterated this week at the AI summit that I visited in Santa Clara. And before I go into the elaboration, I just want to reiterate the importance of visiting conferences and talking to industry specialists about all kinds of things. In this particular case, we focused on the next generation of AI compute and, in general, the compute paradigms that are shifting. And I think it's just a nice example of how we work. And the purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. So this is a good example of explaining also how we actually work and how we gather intelligence. We don't, often Wall Street is portrayed in Hollywood as this cigar smoking master of the universe type people, and that's not how we operate. Maybe some people do. We go. It's hard work. It's listening to people. It's understanding, reading, going to lectures, going back to university. It's constant learning, and it's trying to find the big inflection points where wealth is created. That's our job. That's where we put the money. That's where we try to find employment for our capital. And I think this is a perfect example of, I think it's one of the most important episodes probably for the coming years, because this change in compute paradigm is something very big. Change in compute paradigms create opportunities for wealth creation. And excuse me, this is a perfect example. So what is changing? We have two changes. One is the end of Moore's law, and second, data-centric computing. Let's talk about the end of Moore's law. So for 30 years, Moore's law has been driving compute. In other words, any kind of more complex workloads that were possible or asked for were just solved by putting more transistors on the silicon. Moore's law says every 18 months, we can either lower the cost of the same type of silicon by half, or we can increase or double the amount of transistors on the wafer for the same cost. So this, in other words, we can grow every 18 months. We can double our efficiency capacity. So this worked fine until recently, because we are now getting to a limit where Moore's law doesn't work anymore. So we have to be more intelligent. And this is a beautiful Popperian situation where we have a problem, which is Moore's law is ending just because of capacity constraints. And now we have to do new things. And these new things open up many, many new avenues. One good example is RISC-V. RISC-V is an open source project by Berkeley that is trying to change the instruction set architecture, which is sort of in the middle of the compute stack. If you take the compute stack that starts with the problem, then the algorithm, the program, and then we go down, we sort of leave the abstraction level and get more closer to the silicon, and the instruction set architecture combines the software with the hardware, literally takes a compiler code and turns that into actually executions on the gate level. So the instruction set architecture changed because the instruction set architecture in x86, which was sort of the Intel-driven standard, was very complex and very bloated. To use the word bloated, that's what I heard a lot in the industry, in this industry meeting this week. What it means is that instead of trying to be intelligent and smart and modular and lean about these problems, because we had the opportunity to just put more and more transistors on the silicon, we just kept more complex instruction set architecture. The way, maybe an easy way to understand this is that if you have something like a sort function, or let's say a vector multiplier, you can just put that into instruction set architecture. Just do a vector multiplication. Instead, I think the new way, the RISC-V way, is you do modular. You say, look, we don't have a vector multiplier within the instruction set architecture. We have much more simple components that then can be combined into a vector multiplication. That way you have more flexibility. You're using a lot less power, which is the main constraint actually in this day and age. But I don't necessarily want to, I don't want to talk about computer architecture. This is not a computer architecture lecture by any means. I would never be qualified to do that. What I want to talk about is just that the fact that all these things are actually happening, that in itself is amazing, because it opens up new opportunities for new types of problems, new types of workloads, new types of problem solving, which then create new problems, better problems, and so on and so forth. Fundamentally, what this does, and this is the key, it allows for faster iteration, lower cost iteration, faster the detection of errors, lower cost of errors, and lower cost of error correction. And this is all part of our natural Sharpe ratio concept, or if you want more epistemologically driven, it is part of the Popperian view of the world, which is that if we can iterate fast and compound interest, compound returns are a function of number of iterations. So the faster we can iterate at a lower cost, the faster we can drive new ideas and solve problems and create new problems and so on and so forth. Build innovation stacks, build wealth. We don't even know where, let's say, RISC-V could enable compute that we don't even know about today, because we never had the opportunity to iterate at low cost and be this modular and be at this low cost and also have low cost of error correction and all that. I mean, just one little example, Kirsta Asanovic, the sort of founder of Sci-Fi, which is the big Sci-Fi, which is a big RISC-V company, and also he's the founder of the project. Actually, he's the professor at Berkeley that started RISC-V. The reason he started RISC-V is just to be able to teach compute instruction set architecture in a more modular way to students. I mean, that alone is already screaming opportunity, because you can teach a lot more people basic stuff about the ISA. So instead of being bloated and showing up at a place like Intel and then spend 20 years trying to understand all the bloated stuff, you have the opportunity to start from scratch, understand something in much, much simpler terms, and then create new ideas. So this is, it's almost in a similar realm like we see CRISPR, which is, again, democratization of gene technology and genomics. But let's not go there now. Let's stay on the compute side. So new paradigm, new compute paradigm, great opportunity. And this is the beauty of the situation that we're in. And just as a tangent, I want to say, we spend so much time talking about the macro and about the risk with China and the war in Russia, and all these things are terrible and important, and inflation is a problem and all of these things. But nevertheless, we want to just lean back a little bit, give some hope to people, because we see here in Silicon Valley, right in front of our door, in Santa Clara, in Sunnyvale, in Mountain View, in all these places, Palo Alto, there's a new compute paradigm happening, and it's happening, by the way, everywhere in the world. This is not just here, but here's sort of the epicenter of it. And this is a great opportunity. This is fantastic, and I think we should cherish that as investors. So the second big compute change that I think is happening, and that we saw also at this conference, is what we call data-centric compute. Data-centric compute is kind of the Andre Kapati idea of software 2.0. It just means that instead of writing explicit software which gets executed, we are now writing algorithms which then are fed data, and then the data drives the algorithms to do something. For example, the self-driving car. What that means in particular is that this is now very much along the lines of Onur Mutlu is, and by the way, we've seen that also at the AI conference this week. There is a need for better memory. Better memory interconnect. CXL, one of the protocols which connects CPU with memory, for example, was one of the things which were discussed in the conference. The importance here is the following. The memory is becoming a bottleneck, because on the one hand, you have so much data which now comes in and drives the algorithms, and then you have the problem of just the back and forth, which consumes a lot of energy, or it also consumes a lot of performance, because there's a lot of latency and all these things. So you have to find ways to to build better hardware, to then write better software to enable this data-centric compute. And this is another beautiful example of when we start looking from up the stack and down the stack, we see opportunities everywhere. We see opportunities on the algorithm side, where we have self-supervised reinforcement learning versus supervised learning. We have there was a beautiful presentation by a gentleman that spoke about the constraints in supervised learning where's data. Then the constraint on supervised learning is compute. Now the constraint is power, basically, where we have this new type of learning, which is, let's say, self-supervised reinforcement learning, for example, or those types of learnings where we do more end-to-end learning. So those are important developments on the algorithm side. Then we have, on the programming side, we have scripted languages such as Python and so on and so forth. But now we go down to the ISA. We just mentioned RISC-V, which is a beautiful example. There's other AMDs trying to change the x86 architecture in a much more modular way. We're going towards more modularization, and we're going towards more efficient data-centric compute. And then we can even go further down to the gate level and silicon and all that, but we're not doing that here. The point, again, is that we have this massive opportunity because of the change in compute. And just to end this episode, I just want to remind people that the biggest wealth creation that happened in the last 50 years wasn't Silicon Valley or generally in the compute space. Companies like Microsoft, Amazon, Apple, Tesla, they all changed, created, Google, and the trillion-dollar companies all are based on changing in compute paradigms. Changing compute paradigms. They could be as simple as like with Tesla, where they just created new chips for self-driving cars and then created the self-driving car industry, or Google, which we all know what Google's doing. No matter what, it's a changing, the changing in the compute paradigm. And Amazon was the distributed computing side of things, which drove AWS and the cloud computing space. So we have all these opportunities which are popping up, enabling new paradigms, enabling new big shifts in compute, and big shifts also like in memory, which is part of compute. Basically, we are going up and down the stack and innovating across the stack and driving innovation, driving the possibility for iteration, lowering the cost of iteration, lowering the cost of error, and lowering the cost of error correction. All of these things according to the natural Sharpe ratio concept that we have, and please refer to that in our episodes, prior episodes. All of these developments eventually increase the probability of disruption, increase the probability of wealth creation. This is the key. So to summarize, the big two compute platform changes which are driving new compute paradigms are that we have end of Moore's law and the necessity to think across the stack, particularly on the ISA level, like RISC-V, for example, and data-centric compute, which requires new ways to incorporate memory into the whole compute stack, because we are now driving data into algorithms, and then algorithms execute based on that data. So this is a new compute paradigm, very much driven by the concept of software 2.0 by Andrej Karpathy. But it's a much bigger paradigm than that, because it involves everything. It's not just self-driving cars. Every compute platform in this day and age is driven by data and by the ability to then learn from that data and do something. So, and no matter which compute model you use, which learning model you use, self-supervised reinforcement learning or supervised or unsupervised, they're all driven by the same thing, which is data algorithm execution. And that's the great opportunity. The opening up of the stack and the faster and lower cost iteration opens up the potential for faster wealth creation. Thank you.